Now let us study about this simple example of a Benevolent diagram illustrates the need to distinguish between the structure which is drawn as the baseline of Benevolent diagram and the diagram itself. Here the point here is that the value of bending moment over CD portion CD span is 0. You can wonder why this span CD is having 0 bending moment. Let me explain the reason. When you load this span ACD at loading at the B, because of this load, it will deflect like this. After that, the same rotation it continues here. In this portion CD, there is no load, nothing, so it remains as a straight. That means the CD is not having any bending, so it remains straight because here the same slope at C, this anti-clockwise slope, will be having the same thing here, anti-clockwise slope, so it remains straight. So there is no bending moment at this portion CD. Only the bending moment is between the A and C. That portion is having the bending moment. This you can visualize also. If you take a cut at here, if you take the this portion, right side portion, there is no load, so there is no force, nothing, there is no movement until this support point comes. There is no force, no reaction, nothing, so this is having no load effect, so that's why it becomes straight and there is zero bending moment. And always note that the bending moment diagram is always drawn on the bending tension side of the structure. Here, if you, because of this load, the beam is bending like this, the bottom side of the beam is having tension in this case. So here one golden rule is that if the part of the structure remains straight after loading, no bending moment, it means that this structure, part of the structure CD, after loading, this bends like this but it remains straight. That means there is no bending moment at this straight portion. That's what it's written here. This is one of the golden rule we need to remember. And another golden rule is that the bending moment is always zero at simple support. At these points, the bending moment is always zero at the simple support points. And bending moments resulting from point loads are linear expressions. Therefore, the bending moment diagram consists of straight lines. If you see this bending moment diagram of this one, it will come from like this and then it like this, it will go. It's a straight line. That's what it's written here. The bending moments resulting from point loads are linear expressions. Therefore, bending moment diagram consists of straight lines. If I draw the bending moment diagram, it will look like this along with the straight lines. In addition, the diagram can only change the direction at load or reaction. If you see here, the bending moment is coming like this. After that, it will change the direction at the load point or at the reaction point. That's what it's mentioned here. In addition, the diagram can only change direction at a load or reaction. And here now we will go for an example. We will carry out a qualitative analysis of a proper cantilever. This is a proper cantilever structure. We will carry out the qualitative analysis. We will apply the principle of superposition to examine the effect of fully fixed support at A, and by the notional removal of the moment reaction at A. For example, this is a fixed support, so here for example I want to remove this, release this moment, and we will apply as an external load. Okay, we will apply this MA, considering this as a simply support. Simply support means only two reactions, vertical reaction, horizontal reaction, only it will be getting developed, but we are going to apply one externally the moment, like this is applying at the anti-clockwise direction. Okay, here we can see, considering this as two separate cases, when the load is applied W as a simply supported case, 16A as a simply supported beam, there will be a clockwise rotation at A. If you consider this as a simply supported beam because of this load, it is rotated like this, so there is a clockwise rotation at A. The propped cantilever, however, will have zero rotation at A. If you see the propped cantilever, it will have zero rotation at A. So, and to return to our original structure, we must apply an anti-clockwise moment. If I apply anti-clockwise moment, this becomes straight, there is no rotation. Whatever the rotation is, the corresponding amount of moment if you apply, there will be no rotation. This is clockwise rotation, so we are applying anti-clockwise moment to negate this or to balance this clockwise rotation. Then only we can return to our original structure, proper cantilever. Because this at cantilever point, the rotation is 0. That's why we are applying anti-clockwise moment to uh, reflect this proper cantilever. Okay, so now it is now very apparent that there will be a change of curvature. There will be a change of curvature because initially the curvature is like this, sagging. Because of application of this anti-clockwise moment, there will be a hogging curvature, hogging moment. So there is this curvature, it will be like this, and this curvature it will go like this. So there is a change in curvature. Initially only single curvature, now we have one curve, one bend, one moment, one bending, like a hogging and sagging. So curvature changes. So it is now apparent that there will be a change of curvature in the deflected shape, which is known as the point of contraflexure. Here you can see this point of contraflexure where the change of curvature is can be easily seen. This provides another point of reference between the deflected shape and the bending moment diagram, because bending moment is 0 at the point of contraflexure. Actually, the member is unstressed at the change of curvature. We should note that the member is unstressed at the change of curvature. Here, now we can now attempt to draw a Benevolent diagram. We know that there will be a hogging moment at fixed support EA, like this as shown here. This is recognized by the anti-clockwise reaction. Because of this vertical load applied, there will be anti-clockwise moment at this reaction at the support A that makes the hogging moment. Okay, so because of this hogging moment at the top side of the beam, it will have tension. This is recognized by the anti-clockwise reaction and the identification of tension on the top of the beam from the deflected shape. At the other end of the beam, because of this upward reaction, VB will cause the tension on the underside of the beam. VC will cause bending moment, that will cause tension on the underside of the beam. This hogging moment will cause on the top of the beam, tension on the top of the beam. On the other side, this VB, it will create a moment. That moment is a clock. This one is, if you apply here, VB, it will create like this moment. This also anti-clockwise. So that will, but anyway, that will cause it to go up. So the bottom side only the tension is coming. Okay, the bending moment will be straight line from B until it meets the load point, until it meets the line of action of point load. The Benevolent diagram, it starts from B as a straight line until the point where the line of action of this load point is there, until it meets the line of action of point load. Then this diagram is completed by drawing a straight line like this, because here we have the hogging moment. On the top of the beam side we have the tension, so it is drawn like this, and here at B we have the other side of the beam tension, so we are drawing like this. It will go, the line will be straight until it meets the line of action of the point load, this point load. Then we can connect these two, then we can identify the point where the Benevolent diagram crosses the baseline. That point is called contraflexure. You can understand the bending moment diagram crosses the line at point of contraflexure. This is another golden rule to remember. This line must pass through the point of contraflexure. The line which is connecting like this, that will pass through the contraflexure.